Hello, good evening, sir. Sir, I am Subhajit Bhattacharya from Durgapur, West Bengal. Sir, I have some queries. Can I raise those? My first query is I think, according to the course, I have understood that the interaction volume increases with increasing atomic number. Is it so? Interaction volume increases with increasing atomic number. Okay, so what is okay? In, okay. So higher the density, lower will be the actually interaction volume. Okay, so that was one doubt of me. That is why one assignment I put wrongly. Another question is that is also from assignment that is assignment 5 probably, yes. So that was no, assignment 5 has been here. 6 has not. Assignment 5 deadline is crossed. That was 25th February. Assignment 5. So there was a question that ET detectors are widely used to collect both secondary and backscattered electrons in ACM. Now we have modified the detectors as ETD1, that is normal ET detector, ETD2, ET detector with a negative bias of minus 50 volt, and ETD3, that is ET detector with a positive bias of 10 volt. So it has been stated which of the above detectors will attract secondary electrons. So I answered that normal ET detector and ET detector with positive bias. That is okay. But my confusion with the backscatter electron. In the videos, he has said that with a negative bias, backscattered electrons will also be there because to separate the secondary electrons, we provide a negative bias of minus 50 volt or minus 100 volt so that only backscattered electrons will be there. So accordingly, I opted for the ET detector with negative bias minus 50 volt. But the answer has been only ETD3, that is ET detector with positive bias 10 volt. The question was which of the mentioned detectors will attract all the backscattered electrons. So if you can clarify this, why is it so? Yes, 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 yes. Yeah, that is sure. Yes, yes. Oh, that is why. So as attract has been there, that is why. So secondary electrons also for the case that okay. Oh, so that is why zero, that is a normality detector, that is without any bias. That option is not being given. As attract word is there and all the word is there. Hmm. Hmm. In that case, we will give minus. Okay. But will attract secondary electrons. In that case, the normality detector and 10 volt positive bias detector both are there. So in the backscatter electrons also, these two options could be there. The normality detector and positive bias. So, but in the option only ETD3 is there. That is only with the positive bias of 10 volt. Okay, sir.
So we will start today's session. Hello everyone, welcome to the course Material Characterization by Professor S. Shankaran of IIT Madras. This is the sixth week of the course, live problem solving session for the sixth week of the course. And I am Mayank. I am a research coordinator Department of Electrical Engineering, IIT Bombay. The course is being taught by Professor S. Shankaran who is an associate professor in the Department of Metallurgical and Materials Engineering, IIT Madras. The course plan for this week are various imaging techniques in SEM and okay, I think I put wrong options here. So so these are for fifth week. So this week there are so the options are this for this week. The plan is different con- contrast imaging techniques and tutorial applications of SCM. The this session is happening every Sunday 6 p.m. to 8 p.m. at this Google Meet link. So I will be first showing you some slides regarding this week's topics. So again, the disclaimer that these are AI generated slides, so don't believe everything you see here. So special contrast mechanisms SCM. So like so SCM can give you electrical and magnetic field contrast, which so you cannot accept topography, you can also use that for visualization. So electric field contrast, that is voltage contrast, is used to visualize surface potential variations, and magnetic field contrast are used to visualize internal and external magnetic domains. So typically SCM is used to see the surface topography and and atomic number contrast. So secondary electrons are used for surface topography, and backside electrons are used for contrast based on elemental contrast. But other than that, you can also use it to image electrical and magnetic fields. But these special contrasts are not available in every material. For that, you need special classes of materials such as integrated circuits, insulating materials, and magnetic solids. So electric fields are of you can there can be two types. One is voltage contrast and other is localized charging. And magnetic fields, you can visualize leakage fields and internal fields. So voltage contrast. So the mechanism here is it's very simple. So you take ICs, and so within the SCM chamber itself, you probe this, you connect this IC to your to an electrical circuit, and you apply a potential across different regions of the IC. And what will happen is that, so now the, this so now this region where you are imaging, that is at a certain applied potential, and there's a potential on your detector. So depending on the so this applied potential and your detector potential, there will be a difference in both, and that difference will and that variation in the potential will will affect how how many secondary electrons are pulled into the detector. So that that will be able to using that we'll be able to compare different regions and the applied put and the potential at variations across a surface. Next is localized charging. So this happens either in insulators, or you can take conducting samples and cover it with insulators. So what happens is when you shine an electron beam on it, the electrons enter the insulator and stay on the surface because they stay on the and they are very high energy, so they enter your specimen and stay on the surface because it's insulating, so the electrons cannot move freely inside your material. So they stay near the surface where the beam is shining. And now what happens is now all these electrons start repelling the start repelling the electrons that are now coming, and so they start acting like an electron mirror, and that creates a bright spot bright spot in your image. So this is an art this bright spots in artifact. It is not actually part of your material. It is coming due to these trapped electrons, and this trap electrons create a localized charge here. So this can be used to this can be used to visualize the your insulation strength. Then magnetic field contrast. So the magnetic field, the so you know the formula F equals to minus E V cross B, where B is your magnetic field and V is the velocity of the electron and F is the force. So the and a charge moving through a magnetic field will experience a vector force which can accelerate the electron and also change its direction. So what can happen is you shine your your electrons are coming out of your sample, and if they experience a magnetic field, they can they can be deflected towards or away from the detectors, and that will give you a contrast in your detection image. So so if you have a sample with magnetic domains, that domains having will be having a leakage field and when your secondary electrons are ejected from a sample, they have to move through this field leakage field, and and this leakage field will then deflect then cause a force on the secondary electrons, and they can be deflected. So now they can be either deflected towards your ET detector or they can be deflected away from your ET detector depending on your magnetic field direction. So if they're deflected towards the detector, then the detector will have a bright spot. If you are deflected away, then you will have a black dark spot, and this contrast can tell you the direction of the magnetic domains. Next is internal field. So this was the we were seeing the leakage field that is coming out of your sample. Now, if you want to visualize the internal field that is magnetic field within the sample, for that we use backscatter electrons because they can go deep inside your sample. So depending on the internal magnetic field orientation, the beam is either pushed to the surface or dragged deeper. So, so what can happen is so so either it can push the beam upwards towards the surface, or it can drag the beam downwards deeper inside, and so that will change your interaction volume, and that will directly change your yield of the backscatter yield. So if it is forced towards the surface, then electrons it will be easier for electrons to get out. So you will have more brighter contrast on your reactor. Or if it drags them inside the surface, then very few of the backside electrons will be able to get out of the sample, and that will create a dark contrast. So now we can also use SEM to get crystallographic information. So standard electron imaging is just seeing surface topography, but you can also visualize crystallographic variance in your sample. So the one is your ECCI, that is electron channeling contrast imaging. This relies on atomic density. So in certain direction you will have a very low atomic density, which are called open channels. So since your atomic density is low, the electron is able to penetrate deep into the sample, and if it goes very deep into the sample, it will be very difficult for your electrons to come out. So the backscatter yield becomes low. But if they hit the regions where their density is high, that is closed channels, so denser atomic packing causes your Im- immediate scattering at the surface level itself, and the backscatter yield is higher there. So the path of least resistance determines the backscatter electron yield. And the yield difference between open and closed channels is only 5%. But this 5% is all this 5% modulation is enough to be able to give a contrast in the image, to produce crystallographic contrast in the image. Next is the next is a method called electron backscatter diffraction, or EBSD. It is able to give us the information of the crystallographic planes. So it is also called Kikuchi diffraction. So what it does is that it produces distinct bands of bright and dark line pairs, and these patterns act as unique geometry fingerprint. So they allow for highly accurate quantification of microstructures, gradient orientation, and phase identities. So they are produced by inelastic scattering, which are followed by elastic Bragg diffraction, which forms these lines. So first inelastic scattering happens, and then the electrons they move through the lattice and get diffracted. And if the if the diffraction is closer to the forward direction, then it results in higher intensity. If if it's slightly different, then a slight variation causes a negative diffraction, so it appears as a dark line. So hence you always see your lines in as a pair of bright and dark lines across. So across your background, you will see one excessively bright line and one very dark line. So the intensity difference between the forward scattered and the back diffracted rays creates creates the parallel bright and dark Kikuchi lines. And how these lines are generated is that the diffracted electrons will form a cone called as cosal cone, and this cosal cone will intersect with the Ewald sphere, which is your reciprocal lattice regions, and their intersection will create a parabola, and this parabola is what you see as your Kikuchi line. But because your angle is so small that these parabolas appear as perfectly straight lines. So the anatomy of a Kikuchi band is like, so this is your diffraction plane. If you go plus G on it, you will have a excess line. If you go minus G, you will have a deficient line. So by by measuring the middle of these lines, you can get your diffraction planes. So in a set to get EBSD to generate a usable Kikuchi map, we require highly specific physical parameters. So the specimen stage is tilted to 70 degree so that we are able to produce an extremely flat cone, that is very small alpha cone, which is necessary for the pattern. Also the sample requires a very high defect free surface. So electrolytic polishing is a mandatory step here because you want to produce very highly defect free surface. So so first you probe your sample, and the raw pattern is generated with Kikuchi lines, and then what will happen is your software will have a database of Kikuchi lines depend for different crystallographic data, and that and it overlaps the different lines and tries to match them to find a perfect match, and this gives us the information about what the Kikuchi pattern is about from. And to get a good to get a proper usable data, we want to keep the step size very small, closer to your depending on your grain size. So standard requirement is that you want to capture 2 to 4 different orientation data points per individual grain size. So if you take very large step size, then you will be missing your grains and you will not have enough data points per grain. So next is your inverse pole figure maps. So what they do is they represent exact crystallographic orientations. So this is not an orientation map. This is orientation map. It is not a topographical microstructure map. So it is not giving you surface microstructure. It is giving us orientations of the orientation of different grains. So that is which grain is of which direction. So here you can see three different planes are used: 001, 101, and 111. And so the red is representing your 001, green is representing 101, and blue is representing 111 here. And the and if you see two adjacent grains and see the misorientation angle, you can calculate the misorientation angle between them. So for a 60-degree misorientation means a twin boundary, while a 30-degree orientation means a standard very high angle boundary. And then pole figure maps can give you macro level texture across your sample. So your 001 will look like this, 101 will look like this, and 111 will look like this. So EBSD is a very incredible, powerful tool to get surface crystallography, but the signal is generated exclusively from the top 20 nanometers of the specimen. So it is a surface. It only characterizes the surface layer. Does not characterize the bulk material behavior. For that, you still need X-ray diffraction. Next is your fundamentals applied problems. We will see now. So recap. Let's recap. So first, we see first an electron is generated at the electron gun. So your filament, then they are controlled by electromagnetic lenses. Then there are optics to shape the to give the shape to the beam, and then there's interaction with the target, and then there's a detection in the detection by detectors. So at the gun, so if you have, let's say if you have a accelerating volt of 25 kilovolts and you have to calculate the wavelength of the emitted electrons, how will you be able to do that? So you will be using the formula lambda equals to 1.5 by V plus 10 minus 10 power minus 6 V square per half, where your V is in kilovolts and lambda is in nanometers. So if you do that, so your so you will be able to calculate your lambda. And then so your when the so in your electromagnetic lenses, you squeeze the beam by changing its direction radius. So magnetic field is applied on the electromagnetic lens perpendicular to the electron beam direction. So we can calculate the resulting radius of the electron beam, and for that the formula you will use is R naught, which is radius, equals to 1 by V under root 2m V naught by E. Next is your if your electrostatic lenses. In your electrostatic lenses you have two different you have two different voltage regions, and using Snell's law, you can modify the direction of the beam. So you should be able to get the potential difference by if you have the angles, or if you have the potential difference, you should be able to get your angular difference. So for that, you will use the Snell's law for electrons. Sin r by sin I equals to square root v1 by v2. So when you come to probe shaping, then so the beam geometry give, uh, is given using the brightness of the sample, and so the brightness is given using certain geometrical and electrical parameters. So the formula is your beta equals to 4 IP by pi square dp square alpha square, where IP is your probe current, dp is your beam cross section, and alpha is your convergence angle. That should be able to give your beta. Now you want to see the optical optimum aperture, so that balances your distortions. So your theoretical resolution is given as your r equals to 0.61 lambda by alpha, whereas your spherical aberration gives resolution as CS alpha cube. So in one case you want, so to minimize spherical aberration you want a small aperture, but it also simultaneously worsens your diffraction limited resolution. So for diffraction limited resolution you want a larger aperture. So we want to have a mathematical compromise where the net resolution is optimized. So net resolution is given as sum of both resolutions, R1 plus R2. And if you take the derivative, you are able to isolate the aperture angle. So you get your aperture angle, optimal aperture angle, optimum is proportional to lambda by CS 1 by 4. But ultimately, your minimum probe diameter at the intersection at your surface gives your absolute resolution limit, and that that can be calculated using the formula d mean equals to k into cs power 1 by 4 into lambda power 3 by 4 into ib by beta lambda square plus 1 3 by 8. So that using that you can calculate your absolute minimum probe diameter. Then your depth. Then for depth of focus, we know that depth of focus scales inversely with aperture angle and magnification. So the formula for that is d equals to zero point 0.2 by lambda m, where not zero point 0.2 by alpha m, where alpha is your semi aperture angle and m is your magnification. That will give you d in millimeters. Next is to measure the yield of the sample to get the yield. So the governing equation is given by Kirchhoff's law, that is I is not equal to ISC plus IBSC plus ISC. So SE is your secondary electrons current, BSC is your backscatter electrons current, and SC is your sample current. So from here you can get, so you can calculate your yield. Secondary electron yield will be ISC by I naught, backscatter electron yield will be IBSC by I naught. So that you can see the yield equations here. So backscattered yield is given as eta equals to IBSC by I naught and delta equals to ISC by I naught. So this is a overview of all the equations. You need to calculate different parameters in your SEM. So wavelength of emitted electrons you can calculate here. Then beam radius in the electron through the electromagnetic lenses you can calculate here. Then the change in direction using electrostatic lenses you can calculate using Snell Snell's law. Then the system brightness you can calculate using this formula. What is the optimum aperture you can for minimizing your aberrations you can get from this. The minimum probe size you can calculate using this formula. Depth of focus you can calculate using this formula. And your current distribution and yield you can calculate using this formula. Next we come to some practice questions. Choose the correct option. Statement 1. Channeling contrast comes due to backscattered electrons. Statement 2. Backscattered electron coefficient is dependent on the orientation of a crystal with respect to electron beam. Statement 1 is correct only, statement 2 is correct only, statement 1 and statement 2 both are correct, and statement 2 is a correct explanation of statement 1. Statement 1 and statement 2 both are correct, but statement 2 is not the correct explanation of statement 1. You can write your answer in the chat or speak your answer.
The answer will be C.
That is correct. The answer would be C. So we just studied the channeling contrast is coming from the backscattered electrons, and the reason for that is that the coefficient of backside electrons is dependent on orientation of crystal with respect to the electron beam, because due to the orientation the density density through for directional atomic density will be different. Choose the correct option. Statement 1. Step size in EBSD should be less than the grain size. Statement 2. Each grain gives particular orientation. 1 is correct only, 2 is correct only, 1 and 2 both are correct, and 2 is the correct explanation of 1. 1 and 2 both are correct, but 2 is not the correct explanation of 1. So the correct answer is D. So, so we just said that in EBSD, if you want to have meaningful data, you want the step size to be less than grain size so that you can have multiple points for each grain size. For each grain, you should have multiple points. And also, this statement is also correct that each grain gives particular orientation. but that is not the correct reason why the step size should be less than grain size. So both are correct, but 2 is not the correct explanation of 1. Choose the correct option. Statement 1. EBSD is not a bulk characterization technique for texture determination. Statement 2. XRD is a bulk characterization technique for texture determination. Statement 1 is correct only. Statement 2 is correct only. 1 and 2 both are correct, and 2 is the correct explanation of 1. 1 and 2 both are correct, but 2 is not the correct explanation of 1. That is correct. The answer would be D. So XRD is a bulk characterization technique for texture recognition because XRD X-rays can penetrate deeper can penetrate deeper into the sample. Not, I would say deeper, but they can give you crystal information more deep into the sample for like several microns or 100 microns. But EBSD can only give you surface level information that is up to few nanometers. So hence it's not a bulk characterization technique, but it is also used for texture determination. So both are correct, but 2 is not the correct explanation of 1. Which of the following statement is correct with respect to Kikuchi lines? Formed due to inelastic scattered electrons followed by elastic scattering. Formed due to elastic scattered electron followed by elastic scattering. Formed due to inelastic scattered electrons only. Formed due to elastic scattered electrons only. Which of the four statements is correct? So correct answer to A. So Kikuchi lines are formed by due to inelastic scattered electrons, which are then elastically scattered in diffraction patterns. An accelerating voltage of 40 kilovolts applied to the tungsten filament in SEM. What could be the wavelength of electron? 0.0086 nanometer, 0.0077 nanometer, 0.0061 nanometer, 0.0039 nanometer. So the answer is C. So you have to use the formula lambda equals to 1.5 by V plus 10 per minus into V square per half. So if you put V equals to 40 here, so this value is very, very small compared to this value. So you can neglect it. So it will just become this. And if you solve this, you get 0.0061 nanometers. Dr. Avnish wants to characterize copper sheet as shown in the figure below by using electron backscattering diffraction technique. After the test, he got some results. So you are given the three direct. So 001, 010, 100. So the rolling direction that is x this way is 010. Normal direction that is perpendicular is 1001, and transfer direction which is this is 100. So is this material fully textured, true or false? The answer is A, true. So it is fully textured because you can see in all of the regions, you can see you can get crystallographic data properly. So all of the grains are have proper texture. Which of the following images can be the 100 type pole figure map of the material? the correct answer to this would be B and C, B or C. So, so for 100, the so the 100, the figure, the points come as a square. So they will become in a square pattern. So it would be B or C. Here also they are square, but there you can see two different directional squares are there. So this won't be 100, and here here proper pattern is not created, but we can see here we have proper patterns 100 direction. So the answer will be B or C. In an electron microscope, the electron beam of wavelength 0.0061 nanometer passes through an electromagnetic lens having strength zero point 0.3 Tesla. Calculate the radius of electron beam. 2.248 millimeters, 2.248 nanometers, 3.548 millimeters, 3.548 nanometers. So the answer to A, 2.248 millimeters. So from wavelength you can calculate the voltage, accelerating voltage, that is that you can calculate from this formula. You will get 40 kilovolts. So when you put that in here, so magnetic field you are given as zero point 0.3 Tesla, and voltage you are given as 40,000 electron volts. M is your mass of electron, 9.1 10 power minus 31. E is your electronic charge, which is 1.6 into 10 power minus 19. If we put everything and solve, we will get R naught equals to 2.248 millimeters. So that are all the questions I had for today. Thank you for attending. If you have any doubts, you can ask, or if you want, you can leave the chat.
Hello, sir.
Hello.
In the last problem, lambda is equal to 1.5 by that formula. That would be whole to the power half, no?
What?
1.5 by b plus 10 to the power minus 6 into b square.
Yes.
That whole to the power half would be there.
Yes.
Okay, but here 1.5 by only that to the power half is there.
Yes, because this is negligible.
1.5 to the power half is also there in the formula.
One point
1.5 by this, that whole to the power half was there in the initial formula.
um, this this is from the professor only. I don't know.
Okay, in the lecture, professor has given lambda is equal to 1.5 by t plus 2 to the minus 50 square. That's whole to the power half. But here, in the only in the denominator, whole to the power half is there. So please check what will be the case. And I confirm.